Hello and welcome to this online lecture. My name is Patty Kokish and today we're going to be covering material from your online Math 200 class. We're going to cover Chapter 3 today, which is all about numerically summarizing data. So last week you learned about how to put different types of data into different types of graphics and which types of graphics were best for which types of data. Today we're going to get some numerical summaries of data. So the first thing we're going to talk about is measures of central tendency. And you've probably already heard of some of these. Mean, median, and mode are all measures of central tendency. So let's first determine how to find the mean of a variable from raw data. Now the population mean, which is mu, this is a symbol that you might see, it's a Greek letter, is computed by using all of the individuals in a population. Now since it's a population, that means that the population mean is a parameter, not a statistic. Now the sample mean, which is pronounced x bar, okay, it's just an x with a bar on the top, is computed using sample data. And since it's computed using sample data, it's a statistic, since it's from a sample. But you actually calculate the population mean and the sample mean exactly the same way. It just depends on whether you have a population or a sample. So in this example here, the following data represents the travel time in minutes to work for all 7 employees of a startup web development company. There are 23, 36, 23, 18, 5, 26, and 43. We want to compute the population mean. So all we have to do is we have to take the sum of all of our data points. So if we look at this formula here, we have mu equals the sum of all of our xi's. So this is the sum of all of our observations. So all we're doing is we're just adding everything up in our data, and then we just divide by the number of numbers that we have in our population, which in this case is just 7. So all we have to do is add up those 7 times that I read and divide by 7, and we get 174 divided by 7, which is 24.9. Make sure if you're doing this in your calculator, if you're doing it all at once, you need to put parentheses around your numerator. You also always want to make sure that your answer makes some kind of sense. So we got an answer that's pretty close to 25. If you look at some of our data items, they look to be around that number. If you'd gotten a number of 150, that should kind of ring a bell in your head saying that something doesn't look right, because my numbers are more in the 20s and 30s. Now let's determine the median of a variable from raw data. So the median is the middle of the data when the data is arranged in ascending order. We use a capital M to represent the median. All right, so the important thing here is it's the middle of the data, but your data needs to be organized first. So you have to put it in order and then find the middle. So in order to find it, step 1, arrange the data in ascending order, determine the number of observations, determine the observation that's in the middle of the data set. If the number of observations is odd, then the median is the data value that's exactly in the middle. So for example, if you have a data set that only has 5 observations, then there's only 1 observation that's in the middle. It would be the third one. However, if you have an even number of observations, then the median is going to be the mean of the 2 middle observations. So if the median is the mean, or sorry, if the number of observations is even, then the median is the mean of the 2 middle. So that's just to say that you basically find the 2 middle numbers in your data, and then you add them up and divide by 2. So let's look at that original data again. First thing we need to do is order it. Okay, if it's not in order, we're not going to get the correct median. And then with this one, we have 7 observations. Okay, so that means since we have an odd number, we're just going to have 1 number in the middle. And when you have a small number of data items, you can kind of see exactly what's in the middle. It looks like from here, we just have 23 as our median. Now, the way that you can actually find this is to take 7 plus 1 observations, which gives you 8, divided by 2 and gives you 4. That means that you can count from the left and find the 4th observation. This is useful if you have a lot of data items, but when you have a small number, I'd say maybe like less than 20, it's kind of easier to just eyeball it. Okay, let's say, suppose the startup company hires a new employee. The travel time of the new employee is 70 minutes. Determine the median of the new data set. So again, we order it. Now we have 8 observations. So if you look at this, you can kind of see the two numbers that are in the middle are 23 and 26. So if you look, 23 has three numbers to the left of it, 26 has three numbers to the right of it. So these two are our middle observations. So if we want to find the median, we have to add 23 and 26 and then divide it by 2. And again, make sure that if you're doing this in your calculator, you put parentheses around the numerator and then divide by 2. And you get 24.5 minutes as your new median. So the median increased a little bit when we added a larger number. But one thing to point out is what the meaning of resistant is. So this data represents the travel times, okay? And let's suppose that a new employee is hired who has a 130-minute commute, okay? What is the impact of the value on the mean and the median? So 130 minutes is clearly much, much higher than any of these other observations. It's probably going to be an outlier. So if you recalculate this, well, our previous mean was 24.9, our previous median was 23. And if we do it again with this 130 minutes, our median is going to be 24.5 because we end up with, I think, 23 and 26 in the middle. The mean, though, is 38, so it increased by quite a bit here. A numerical summary is considered to be resistant if extreme values, meaning really large or really small values relative to your data, does not affect its value substantially. So if you think about what we have here, the median is pretty much unchanged by this 130-minute commute, so it is considered resistant. The mean, however, does increase by quite a bit when we just add this one kind of extreme observation, so the mean is not resistant. So what we have on this page is what type of distribution you might have and which numerical summary you'd like to use. So if you have a distribution that's skewed left, which we're going to talk about in just a minute, that means that the mean is substantially smaller than the median. Okay. If you have something that's symmetric, then the mean and the median are approximately equal. And if you have something that's skewed right, then the mean is substantially larger than the median. So if you look back here, I think we talked about distributions in another chapter, but just to review it kind of quickly, we name these distributions skewed left, skewed right, based on where their tail is. So if you look, the tail is on the left, so this is a graph that's skewed left. And then the other thing you can remember is that the mean is always closer to the tail. So if you look, the tail's on the left, the mean is closer to the left. And then the median is always closer to kind of this peak in your data. When you have something that's symmetric, that means we could fold it in half. It would look the same on both sides. The mean and the median are the same. And then if you have something that's skewed right, that means you have a tail on the right, okay? And the mean is closer to that tail. So the mean is on the right. And then the median is closer to the peak. So let's look at this following data. It represents the asking price of homes for sale in Lincoln, Nebraska. So there are a bunch of homes here. They're listed in order. It looks like from about 80,000 to 350,000. We want to find the mean and the median, and then identify the shape of the distribution using the mean and median and verify the result by drawing a histogram. So with this amount of data, you probably want to use some kind of statistical software. So my suggestion would be either to use StatCrunch, which lives inside of your MyMathLab homework. Anytime you have a data set in MyMathLab on your homework, you can click on, there's like a little kind of box at the top right of the data set, and you can do open in StatCrunch, and that will allow you to do things like create histograms, create frequency distributions, calculate mean, calculate median, all of that good stuff. So the mean asking price when we calculate it is 168,000, and the median is 148,000. So since the mean is larger than the median, and the mean is always closer to our tail, that means the mean is going to be on the right. So we would conjecture that the distribution is probably skewed right. And if we look at a histogram, it does kind of confirm that conclusion that we made. So if we kind of think of drawing like a curve above this, you're going to end up with a tail on the right, so it would be skewed right. Okay, objective 4 is to determine the mode of a variable from raw data. Now, mode is kind of our third measure of central tendency, and it's just the most frequent observation that occurs. Now, it is possible to have no mode, okay? You could have one mode, or you could have multiple different modes. It just kind of depends on the situation. If no observation occurs more than once, then we say that the data set has no mode. So one kind of nice thing that we can do with mode is use qualitative data. All right, so when we're finding mean or median, we can't really use qualitative data because we can't really assign a numerical value, but mode is useful when we have qualitative data because we can still find a mode of it. So the data on the next slide represents the vice presidents of the United States and their state of birth. So if you see here, John Adams, born in Massachusetts. See if there are any from Indiana. Yeah, Thomas Marshall, born in Indiana. Dan Quayle, Indiana. So what we can do is we can create kind of a frequency distribution here, all right? And you'll quickly see New York is kind of standing out. It has 8, okay? So that means that the mode is New York because it occurs the most often. Now, there are other observations that occur more than once, like Kentucky occurs 4 times, Massachusetts, Vermont, and Ohio each 3, but we do not include them as part of the mode. The mode is the most often, okay? So in this case, it's New York. Now, if we had another state that also had 8 observations, let's say we had 8 in Massachusetts and 8 in New York, then Massachusetts and New York would have been our modes. We would have had more than one. So here is kind of a summary of the measures of central tendency, how you compute them, how you interpret them, and when to use them. So let's just go through this. The mean we find by taking the sum of all of our observations and dividing the number of numbers. Okay, so we take all of our numbers, add them up, divide by the number of numbers, and that works for either the population or the sample. It's interpreted kind of as the center of gravity. And then we use it when our data is quantitative and the frequency distribution is roughly symmetric. Now the median, in order to compute it, you arrange your data in ascending order and divide the data set in half. So we find the observation that gives you the lowest half and the highest half. This divides your data into a bottom 50% and a top 50%. When the data is quantitative and the frequency distribution is skewed either left or right, that's when we want to use our median. Now mode, for example, you just tally all of the observations that occur the most, and it's the most frequent, okay? And when the most frequent observation is desired, then the mode would be your measure of central tendency. It's not used particularly often, but it is useful when the data is qualitative. Okay, so that was everything with measures of central tendency. Now we're going to talk about measures of dispersion. Now, if you think about something dispersing, you're probably thinking about it kind of spreading out, and that's exactly what dispersion is. So one measure of dispersion that you've probably heard of before is the range. Range is pretty easy to calculate. All you have to do is find your largest data value, find your smallest data value, and subtract. That's it. So you take large minus small, or high minus low, however you want to think about it. So we have these 7 employee times again. If we want to find the range, we know that the lowest observation is 5 and the highest, I think, looks like 43. So in order to find the range, we just take our highest value, 43, and subtract our lowest value, which is 5, and we get 38 minutes. Okay, now if we want to determine the standard deviation of a variable from raw data, I would suggest that when you're actually doing this, you use technology, which I can talk about in just a minute, but let's go through the formulas that we have here. So the population standard deviation of a variable is the square root of the sum of squared deviations around the population mean divided by the number of observations in the population, which is n. That is to say that it's the square root of the mean of the squared deviations about the population mean. Now, it's symbolically represented by the lowercase Greek symbol sigma, which looks like this right here. And here's the formula right here, okay? So what you do is you take the summation of your xi's minus your mu's, which is your population mean, squared, and then you divide by n. So here's a computational formula that also exists. And this is a little easier basically to just use to compute it if you're doing it by hand. And what you do is you take all of the observations and you square them and you sum them up. So that's this piece right here. So take your observation, square it, sum it, and then you subtract. You take all of your observations and you add them first, and then you square that number. You divide it by your sample size and then divide that entire thing by your sample size again and take square root. And sorry, I said sample size here. This is population size because we're talking about population standard deviation, not sample. So it's big N, which is population size. Okay, so if we have this population here of our 7 employees, we can find the standard deviation. Now what we can do is we just type in our xi's, we find our mean, we subtract xi minus mu, we square those observations, and we find that we get 902.8571. And then we use our formula here. We divide that by 7, which is our population size, and take square root, and we get 11.36. Now, one thing I'd like to point out is that when you're doing your homework, or if you have a graphing calculator, that's great. One thing you can do is you can put all of these observations into your graphing calculator, and you can follow the directions that are in the back of the 3.2 section in your book. So if you navigate to your book, either your ebook or a physical textbook, you're going to look at where the 3.2 exercises are, and then it's the page after that. It gives you a technology step-by-step, and what you're going to want to do is probably read the steps for finding the standard deviation using your calculator, and maybe also StatCrunch for when you're doing your homework. That'll make your life a lot easier. So what you'll do is you'll enter this data, and then you'll ask for the population standard deviation, and it will just give you this 11.36. Now the sample standard deviation is very, very similar, okay? All you really have to do is kind of the same thing, take xi minus x bar squared, add it all up, but instead of dividing by your population size, you divide by n minus 1. N minus 1 is called degrees of freedom, okay, and that is explained pretty well in your textbook. But if you think about it, if you think about maybe I have a class and I'm passing out all different types of candy. If we think about kind of going around the class, the first person, they have freedom to choose which piece of candy they want, and so does the second person, and so on. But if I only have enough candy for everyone in the class, the last person doesn't have freedom because they just get stuck with whatever piece of candy is left. So that's kind of the idea behind degrees of freedom. That's like a real world example of how you can think about degrees of freedom. But basically the last observation is just forced to be what it is. Now a formula that's equivalent to the previous one is the computational formula, and that looks a lot like the other computational formula. We take our xi's, square them, sum them, subtract whatever we get when we sum all of our xi's, and then square, divide that by little n, and then divide the entire thing by little n minus 1. And again, n minus 1 is the degrees of freedom because the first n minus 1 observations have freedom to be whatever value they wish. So the first n minus 1 people can choose any candy they want, but that last value, the nth value, has no freedom. It must be whatever forces the value to this. It must be whatever value forces the sum of the deviations about the mean to equal 0. So all of the sums of our deviations around the mean has to equal 0, so that last observation is forced to be whatever number makes that happen. So if we want to compute a sample standard deviation, we could look at a sample from our web development company. And really, if we want to use the computational formula here, all we have is our xi's, which are 5, 26, 36. We create a column where we've squared them. We add up these columns, so we have 67 and 1997, and then we just use our computational formula. So for the first one, we take the sum of all of the xi's squared, and we got 1997. We subtract the sum of the xi's, which is 67, and then square it. Divide by 3 since we have 3 observations, and we divide that entire thing by 2 because we have 3 minus 1 degrees of freedom. And take the square root, and you get 15.82. Again, I would suggest definitely doing this in StatCrunch, especially if you have a large number of observations, and then also learning how to do it on your graphing calculator so that you're able to use it on exams. Now, one thing you can do is you can also determine something called the variance, okay? Now, the variance is pretty easy to find because really we've already done standard deviation. So the variance is just the square of the standard deviation. So the population variance is just sigma squared, and the sample variance is just s squared, since sigma and s are our population and sample standard deviations. So if you recall, the population standard deviation for that first data that we looked at, our sigma, was 11.36. So that means that the variance is just 11.36 squared, which is 129.05. Another option is you can use the standard deviation formula and then just not take the square root at the end. That will result in the same variance. Sample standard deviation that we had was 15.82, and then our sample variance is going to be 15.82 squared, which is 250.27. Okay, objective 4 in this section is to be able to use the empirical rule to describe data that's bell-shaped. So the empirical rule you may have also heard of as the 68, 95, 99.7 rule. And those are three important numbers that you do need to know. So if a distribution is roughly bell-shaped, then what we know is that approximately 68% of the data is going to lie within one standard deviation of our mean. Now, approximately 95% of our data is going to lie within two standard deviations, and then approximately 99.7, or pretty much all of our data, is going to lie within three standard deviations of the mean. So you can also use the empirical rule based on sample data with x bar used in place of mu and s used in place of sigma. So if we look at this right here, we have our mean in the middle, okay, and then we subtract and add standard deviations. Now, if you look here, if we have mu in the middle and we subtract and add a standard deviation, that means we're within one standard deviation. That's this whole area right here. That is going to be 68% of our observations right in here. Now, if we take our mean and we add and subtract two standard deviations, we expand it a little further, so it includes these pieces here. That's going to be 95% of our observations. And then if we go all the way and do three standard deviations to the left and the right, we have 99.7% of our observations. Now you'll see we still have these tiny little tails with a few observations in them, but it's not very much, okay? Now the other thing to keep in mind with this curve is this is symmetrical. So since we know that 68% is within this area right here, if we just want to figure out this chunk right here, which is kind of highlighted by these black and the blue border lines, all we have to do is take 68% and divide it by 2, and that gives us 34. Now, in order to get maybe a little piece like this, you'd have to think a little harder. So for this one in particular, we'd take 95 and subtract this 68. So basically, we're covering up this whole middle area, and we're just left with this piece and this piece. And when we do that, we'd get 27. And then we'd divide that by 2 because we have a piece over here and a piece over here. So you'd get 13.5% for each. The other thing to keep in mind is that the entire thing is going to be 100%, including these little tails, because we're going to have all observations somewhere. Okay, so the following data represents the serum HDL cholesterol of the 54 female patients, of a family doctor. So they're given here. We want to compute the population mean and standard deviation, draw a histogram to verify the data is bell-shaped, determine the percent of all patients that have serum HDL within 3 standard deviations of the mean, and then answer some other questions as well. So using a graphing calculator, or you could use StatCrunch, you would find that the mean is 57.4 and the standard deviation is 11.7. And if we draw a histogram, it looks pretty good. It looks pretty symmetrical. So what we're going to do is we're going to put our 57.4, which is our mean, smack dab in the middle of our chart, and then we're going to add and subtract our standard deviation, which, if I look back, was 11.7. So we take 57.4 and add 11.7, add 11.7, add 11.7, take 57.4 and subtract 11.7, subtract and subtract, until you have all of these filled in. So according to the empirical rule, 99.7% of all patients that have serum HDL within 3 standard deviations of the mean. Now, if we want to figure out how many patients are between 34 and 69.1, what we can do is we can look at our chart here. From 34 to 69.1, we're going to have a piece that has 13.5, 34, and 34. And if we add those up, we get 81.5% of all patients. Now, let's see, what is this one asking? Between 34, oh, okay, so this is asking how many out of the 54 are going to have that. So in order to calculate that, we look back at the original data and we would count and we'd see that 45 out of our 54 patients had a serum HDL cholesterol reading between 34 and 69.1, which is 83.3. That's pretty darn close to our 81.5 that we kind of predicted. Now, it's important that you either understand how these numbers are calculated so that you're able to fill them in on a test, or that you at least know the 68, 95, 99.7 rule. So the 68, 95, 99.7 rule allows you to get to all of these numbers. But if you're not understanding where these numbers are coming from, one thing would be to maybe watch additional videos to kind of explain the normal distribution. Another option that you have, though, would just be to memorize these various pieces. I'm going to suggest that you don't do that, though, because I think it's more time consuming and it is a valuable concept to understand. Okay, objective 5 in this section is to use Chebyshev's inequality to describe a set of data. So Chebyshev's inequality just says that for any data set or distribution, at least 1 minus 1 over k squared times 100% of the observations lie within k standard deviations of the mean, where k is any number greater than 1. That is, at least 1 minus 1 over k squared 100% of the data lie between mu minus k times sigma and mu plus k sigma for k greater than 1. You can also use Chebyshev's inequality based on sample data. So let's use the data from the previous example to determine the percentage of patients that have a serum within 3 standard deviations of the mean. So if we'd like to do that, we take 1 minus 1 over 3 squared times 100%, and this gives us 88.9%. And then determine the actual percentage of patients that have serum HDL between 34 and 80.8. And if we look on the actual data, we get 52 and 54, that's 96%. So Chebyshev's gives you a minimum, okay? And then if we look at the actual data, we can see what our actual percentage is. Okay, let's talk about some measures of central tendency and dispersion from grouped data now. So the first objective is to approximate the mean of a variable from group data. Now, we've discussed how to compute descriptive statistics from raw data, so that's when you're given all of the observations, but often the only available data has already been summarized in some kind of frequency distribution. So you can't find exact values of the mean or standard deviation, but you can approximate them using techniques that we're going to discuss. So if we want to approximate the mean of a variable from a frequency distribution, we can do it for the population mean by taking the sum of all of the xi's times their frequencies and divide it by the sum of all of the frequencies. For the sample mean, we do the exact same thing, except we denote it with x bar instead of mu. Xi is going to be the midpoint or value of the ith class. So since we don't know the actual observations, if we have kind of class widths, then we take the midpoint of that class width and then multiply it by the frequency. Fi is going to be the frequency of that class, and then n is just the number of classes. So if we look at this data here, the National Survey of Student Engagement is a survey that, among other things, asked first-year students at liberal arts colleges how much time they spend preparing for class each week. The results from the 2007 survey are summarized below. Approximate the mean number of hours spent preparing for class each week. So we didn't have anyone who didn't prepare at all. We had 130 students who prepared 1 to 5 hours, 250 students who prepared 6 to 10 hours, and so on. So we've rearranged this data so that it's vertical instead of horizontal. We added up all of our frequencies and we got 1,000. That's the number of people that were surveyed. And then what we did is we took the mean of each of our classes. So from 1 to 5, the mean would be 3, 6 to 8, the mean would be 10, 11 to 15, the mean would be 13, and so on. And then we multiplied the frequency times our mean. So we take 130 times 3, that gives us 390, 250 times 8 gives us 2,000, and so on. And then once we have all of those values, we add them all up, we get 14,250. And we divide that by the number of numbers that we have. So we get 14.25 as our median. Now, if you look at the actual data, the bulk of our data is kind of within maybe this section, okay, right here. And if you look in the middle of this section, 14 is somewhere in the middle there. So that answer makes sense. If we'd gotten a mean of maybe 27, 28, 29, 30, something like that, that should probably seem a little high to you. And if we'd gotten a mean that was as low as maybe 3 or 4, that should also kind of ring a bell that maybe that's too low, because what we're looking at is we're looking at all of this data right here, and the middle is probably somewhere between our 11 and 20. Now, if we want to compute the weighted mean, which we can read as x bar with this little sub w of a variable, we multiply each value of the variable by its corresponding weights, and then add these together and divide by the sum, or divide this sum by the sum of the weights. So this looks a little confusing. It's not this difficult in practice, though. All you do is you take the weights, multiply by the observations, and then divide by the sum of all of the weights. So let's say Bob goes to By the Way nut store and creates his own bridge mix. He combines 1 pound of raisin, 2 pounds of chocolate-covered peanuts, and 1.5 pounds of cashews. The raisins cost $1.25 per pound. Chocolate-covered peanuts cost $3.25 per pound. And the cashews cost $5.40 per pound. What is the cost per pound of this mix? So in order to do this, all we do is we take his 1 pound of raisins and multiply it by the cost, so that's 1 times $1.25, his 2 pounds of peanuts and multiply it by the $3.25, and then his 1.5 pounds of cashews and multiply it by the $5.40. So we multiply, add, and then we divide that entire thing by the sum of all of the pounds. So that's 1 plus 2 plus 1.5. So if we multiply and add these all up, we get 15.85. We're going to divide it by 4.5, and we get $3.52. So that's going to be the cost per pound of this mix once he's kind of mixed everything together. Okay, objective 3 is to approximate the standard deviation of a variable from grouped data. So in order to do this, you can either do it for a sample or a population. It's pretty much the same thing. You just take your xi's minus your mean, okay, so it's either mu or x bar. You square those and multiply by their frequency, and then you add them all up. And then you divide by, if you're doing population standard deviation, you divide by the sum of the frequencies. If you're doing sample standard deviation, you divide by the sum of the frequencies, but you subtract 1 from it. Xi is going to be the midpoint or value of the ith class, and f is going to be the frequency for that class. Now there is an algebraic equivalent for the population standard deviation, and if you already have some of these metrics, then this might be a little easier. So this is kind of just an additional formula that can be used. So if we look back at our data that had our study times for our 1,000 students, if we look at this, we have some extra things that have been added here, okay? So we already did our xi minus our x bar. X bar we just found, okay? That was, I can't recall, 14 point something. Looks like, let's see. Oh, that was back a little ways. I won't scroll to it. I can find it. Yeah, I think it was 14.25. So if you look, we take our xi minus our x bar, xi minus our x bar, and so on all the way down. And then we square it and multiply by the frequency. This whole column is just going to be 0 because we have no observations in it, so it does not really matter. Here we take our xi minus our x bar, which is our negative 11.25. We square that, and then we multiply by the 130, which is our frequency, and we get 16,453. We do this all the way down, and you add them all up, you get 65,687.5. So in order to calculate our sample standard deviation, we take our 65,000 and we divide by 1,000, which was our sample size, minus 1, so 999. When we divide it, we get 65.8. So that's going to be our variance. Now, if we want to find our sample standard deviation, we take the square root of our variance. So we take square root of 65.8 and we get 8.1 hours. Okay, next we're going to talk about measures of position and something called outliers. I talked very briefly about outliers before, but it is an important concept to understand. So the first objective in this section is to determine and interpret z-scores. Now, z-scores represent the distance that the data value is from the mean in terms of the number of standard deviations. In order to find the z-score, you subtract the mean from the data value and then divide by the standard deviation. Now, there is a formula for population and sample z-scores, but they're exactly the same. All you have to do is take x minus your mean. So when you have a population, your mean is mu. When you have a sample, your mean is x bar. And then you divide by your standard deviation, which is S if you're talking about a sample, sigma if you're talking about a population. Now the z-score is unitless. It has a mean of 0 and a standard deviation of 1. So the mean height of males 20 years or older is 69.1 inches with a standard deviation of 2.8 inches. The mean height of females 20 years or older is 63.7 inches with a standard deviation of 2.7 inches. Data is based on information obtained from the National Health and Examination Survey, so who is relatively taller? We can ask if Kevin Garnett is taller, whose height is 83 inches, or Candace Parker, 76. So we're talking about relatively. Obviously, Kevin is taller in terms of absolute numbers, but maybe Candace is taller, given the statistics for women. So we're going to calculate, Kevin Garnett's first. So we take 83 minus 69.1. Make sure if you're doing it in your calculator all at once, you put parentheses around this. Divide by 2.8, and you get 4.96. Now Candace Parker, we take her 76 minus 63.7 because that was the mean for women, divide by 2.7, and we get 4.56. So Kevin Garnett's height is 4.96 standard deviations above the mean. Candace Parker's height is 4.56 standard deviations above the mean. So that means that Kevin Garnett is relatively taller because he's relatively further from his mean in a positive direction. Now, you can get negative z-scores. Negative z-scores are going to happen when you have observations that are below the mean. So positive z-score means you're above the mean. Negative z-score means you're below the mean. Okay, objective 2 is to be able to interpret percentiles. So percentiles are something that you have probably seen in your everyday life. Probably if you have children, you've definitely heard it from the doctor. Your child is in the 75th percentile for height and the 80th for weight, something like that. Or maybe they're talking about head circumference, whatever it might be. In addition to that, you've probably already heard about it when you took maybe the SATs or some other kind of standardized test. Typically, when you get your results, they also give you a percentile. And that just tells you how you performed compared to other individuals who took that same test. So the kth percentile here, denoted P of k, or pk sub k, of a set of data is a value such that k% of the observations are less than or equal to the value. So if we look at this, the Graduate Record Examination, or GRE, is a test that's required for admission to many U.S. graduate schools. The University of Pittsburgh Graduate School of Public Health requires a GRE score no less than the 70th percentile for admission into their human genetics, MPH, or MS program. Interpret this admission requirement. So in general, that would mean that the 70th percentile is a score such that 70% of the individuals who took the exam scored worse and only 30% scored better. So that means that in order to be admitted to the program that they were talking about, an applicant has to have scored as high or higher than 70% of the people who took the GRE, or put another way, they're in the top 30%. So when you're thinking about percentiles, the way to kind of remember it is that if you're talking about a test score, you want a large percentile. You want as close to 100 as you can get. That means that you did very well comparatively. Okay, we're also going to learn how to determine and interpret quartiles. Now, if you already understand how to find the median, then quartiles are really, really easy to find. Quartiles actually divide your data into fourths, or 4 equal parts. Now, the first quartile, we denote it with Q1, divides the bottom 25% of the data from the top 75%. So the first quartile is equivalent to the 25th percentile. Those two things are the same. The second quartile divides the bottom 50% of the data from the top 50%, so the second quartile is called the 50th percentile. Now, hopefully you kind of already recognize 50th percentile, that's actually your median, it's your middle number. Now, the third quartile divides the bottom 75% from the top 25%, so that the third quartile is equivalent to the 75th percentile. So we have first, second, and third quartiles equivalent to 25th, 50th, and 75th percentiles. So if you look at this right here, we're going to have a smallest data value and a largest data value. Q2, which is your median, is going to be smack dab in the middle. Half of your data is below it, half of your data is above it. If you look at the bottom half of your data, Q1 is the median of that. So 25% are below within the bottom half, and we have 25% to the median and the additional 50% over here. So 25% are below, 75% are above. If you look at Q3, that's the median of your upper half. So 75% of your data is below, 25% is above. So if we want to find quartiles, we follow pretty much the same steps that we used when we were finding the median, which is to arrange the data in ascending order, determine the median, and then you divide the data set into halves, the observations below the median and the observations above the median. The first quartile is going to be the median of the bottom half, and then the third quartile is going to be the median of the top half. So a group of Brigham Young University, Idaho students collected data on the speed of vehicles traveling through a construction zone on a state highway where the posted speed was 25 miles per hour. The recorded speed of 14 randomly selected vehicles is given below. We want to find and interpret the quartiles for speed in the construction zone. So it's already in order, so all we have to do is just look at it. I'm not sure why it's not given on that page again. I apologize for that. And if we look in the middle, let's see, 14 randomly selected, so if I count 1, 2, 3, 4, 5, 6, 7, here's one of my middle observations. 1, 2, 3, 4, 5, 6, 7, here's the other. So my middle is 32 and 33, so if I add those up and divide by 2, my median is going to be at 32.5. Now, the median of the bottom half is going to be the first quartile. So if you look at the bottom half of your data, you do include the 32. You do not include the actual median, though. So if the median was just one number in the middle, you do not include it in your bottom half or your top half. And when you calculate it by adding two numbers and dividing by 2, you include those two numbers. You include one in the lower half, one in the upper half, but you don't include the actual calculated median. So if you look at this, this is our bottom half of our data. And now we find the middle observation, it's 28. So that's our first quartile. So the median of these 7 observations is 28. Therefore, quartile 1, or the 25th percentile, is 28. The median of the top half of the data is going to be the third quartile. And if we look at the third quartile, it would have been 38 if we had pulled up that data. It would just be the number in the middle of the top half. So that means 25% of the observations are below 28, and only 25% are above 38. So that's what's given right here. 25% of the speeds are less than or equal to the first quartile, which is 28 miles per hour, and 75% of the speeds are greater than 28 miles per hour. 50% of the speeds are less than or equal to the second quartile, which is 32.5 miles per hour, and 50% of the speeds are larger than that. 75% of the speeds are less than or equal to the third quartile, which is 38 miles per hour, and 25% of the speeds are greater than 38 miles per hour. Objective 4 is to determine and interpret the interquartile range. So interquartile range is often abbreviated IQR. It's the range of the middle 50% of the observations in a data set. That is to say that the IQR is the difference between the third and the first quartiles, and it's found just by subtracting those things. So all you have to do is take Q3 and subtract Q1. So in our case, we had 38 as Q3, 28 as Q1. So 38 minus 28 gives you an interquartile range of 10. So that means that the range of the middle 50% of the speeds of cars traveling through the construction zone is 10 miles per hour. So let's suppose that a 15th car travels through the construction zone at 100 miles per hour. How does this value impact the mean, median, standard deviation, and interquartile range? So we're not going to redo all of these calculations by hand, but what you can see is these are the ones that we've already calculated without our 15th car. And then if we add in that 15th car going 100 miles per hour, we can see how these numbers change. And if you look, the mean, it increased by quite a bit. Standard deviation increased by a lot. Median increased just barely, and interquartile also increased just by a little bit. So if you have a symmetric distribution, then you want to use the mean and the standard deviation. If you have a distribution that's skewed left or skewed right, like it would be in this case with this 100 mile per hour outlier, you're going to want to use the median and the interquartile range in order to describe your data. The median and the interquartile range are both resistant to outliers. Now, in order to check a data set for outliers, what you want to do first is find the first and the third quartiles, then find the IQR, and then determine something called the fences. The fences basically serve as cutoff points for determining outliers. So in order to find your lower fence, you start at Q1 and you subtract 1.5 times your interquartile range. In order to find your upper fence, you take your Q3, which is your third quartile, and you add 1.5 times your IQR. If the data is less than the lower fence or larger than the upper fence, then it's an outlier. So let's check our speed data for outliers. The first quartile was 28 and the third was 38. The interquartile range was 10. So the lower fences, we take our 28 and we subtract 1.5 times 10 and we get 13 miles per hour. Upper fence, we take our 38 and we add 1.5 times 10, which was our interquartile range, and we get 53. So there aren't any values that are less than 13 or greater than 53, so there are not any outliers. And this is using our original data. This would certainly be different if we included our 100 mile per hour person. Okay, now section 3.5, this is the last section. This talks about the 5-number summary and box plots. And basically what it does is it just takes all of the information that we just learned in 3.4 and puts it in a different format, okay? So in order to compute the 5-number summary, you just need to basically find these 5 summaries. You need to find the minimum, which is really easy. That's just your smallest observation. You also need to find the maximum, which is your largest. You find the median, that goes in the middle, and then you find your first quartile and your third quartile. So it's just given in this order, and that would be your 5-number summary. So every 6 months, the United States Federal Reserve Board conducts a survey of credit card plans in the US. The following data are the interest rates charged by 10 credit card issuers randomly selected for the July 2005 survey. Determine the 5-number summary. So here we have our rates here. Pulaski Bank and Trust Company, 6.5%. That looks like our lowest, and our highest, it looks like these two are a tie. Wells Fargo Bank and First Bank of Colorado, both at 14.4%. Oh wait, there's a 14.5 down here, Bar Harbor Bank and Trust Company. So we're going to write the data in ascending order first, 6.5 to 14.5. Smallest is 4.5, so that's going to be our min. Largest is 14.5. The median, or our second quartile, looks like it's the number between these two, which is going to be 13.6. And then if we look at our median of our lower half, we get 12.0. Median of the upper half, we get to 14.4. So in order to write our 5-number summary, we just put our minimum, which is 6.5, our first quartile, which is 12.0, our median, which is 13.6, our third quartile, which is 14.4, and then our maximum, which is 14.5. Now what we can do, once we have those, is go ahead and draw and interpret a box plot. So once you have your lower and your upper fences, which we've already talked about calculating, you can determine if there are any outliers. So you draw a number line that's long enough to include the maximum and the minimum values that exist in your data. You insert vertical lines at the first quartile, the median, and the third quartile, and then enclose those lines in a box. Then you label your lower and your upper fences, which you've already found. Draw a line from Q1 to the smallest data value that is larger than the lower fence, and draw a line from Q3 to the largest data value that is smaller than the upper fence. Those lines are called your whiskers. And then any data values that are less than the lower fence or greater than the upper fence are considered outliers, and you put them on the chart by actually putting a little asterisk. So if we look back at our data, we already found our minimum, maximum quartiles. Now we want to find our lower and our upper fences for our interest rates. So we take Q1, which was 12, and we subtract 1.5 times IQR. Interquartile range is Q3, which is 14.4 minus 12, and that gives us 2.4. So if we take 1.5 times 2.4 and then subtract that from 12, you get 8.4% as the lower fence. For the upper fence, we take Q3, which is 14.4, and add 1.5 times your interquartile range, which is 2.4. So you take 1.5 times 2.4, add it to 14.4, and you get 18.0. So if we look for our step 2, what we do is we draw a vertical line at our first quartile, which is 12, a vertical line at our median, which I don't recall off the top of my head, somewhere around 13.5, and then a vertical line at our third quartile, which is 14.4, and then we just enclose it in a box. And then what you do is you draw a whisker from the lowest observation that is within your fence, which looks like it's just below 10, okay, and the highest observation that's below your upper fence, which looks to be about 14.5. I believe that was our highest observation. And then what you'll notice is that our fences are 8.4, which is going to be over here, and 18.0, which is over here. this 6.5 or 6.4% interest, I don't remember what exactly it was, that is definitely a lower outlier, so we mark it by putting an asterisk there. You can also use a box plot and the quartiles to help you describe the shape of a distribution. So if you look at this distribution that we have right here, this is definitely skewed right based on looking at the histogram because the tail's on the right. And if you look, this whisker has kind of a long right-hand tail, so that kind of indicates that it's skewed right as well. This one right here looks pretty symmetric, okay, so there's no skew there. And this one has kind of a long tail on the left, okay, just like the histogram does, so that one is skewed left. Interest rate box plot does indicate that our distribution was skewed left a little bit. If we look, we definitely have kind of a long whisker over here.